All right, welcome back to the last one we'll go through for this week. It's 3.4, transformations of cubic and quartic functions. Cubic functions are x to the power of 3, quartic functions are x to the power of 4. And we're going to transform them. If you remember our transformations from before, we had a, k, d, and c. So we're going to transform those functions based on a, k, d, and c, and they still apply the same way. Currently, we've transformed linear functions, quadratic, root functions, reciprocal, exponential, and absolute value functions in grade 11 and grade 12 now. And what we're going to do is we're going to transform these here and show that this rules still apply. So what we're going to do is fill in the table of values, just show what the base function looks like, and that what we'll do over here on the left is create the basic coordinates. So negative 2 to the power of 3, we have negative 8, negative 1, 0, 1, and 8. And if I sketch this function over here, we'll end up having a graph that looks like this, and we talked about this before. It's a twist, so we should end up with something that looks like that. For a quartic function over here on the right, same idea. We talked about this before in the last lesson as well, but when I take negative 2 to the power of 4 is positive 16, 1, 0, 1, and 16, and when I plot these points onto the graph, we know that it looks like a U shape, a little bit flatter around the origin compared to a quadratic. However, those are our base points, and that's what the function looks like. We might remember that as the exponent gets larger for either of them, whether it's odd on the left or even on the right, it's just a little bit flatter around the origin. So we're going to transform these two equations based on AKDC. So as I scroll down, we have our basic transformations that we're already familiar with: AKDC, vertical and horizontal stretches and compressions, as well as reflections over the x-axis and y-axis, and D and C, which are our translations, which are just shifts to the left, right, up, or down. You might remember when we transformed points before, basically what we did was we had our basic points from the parent function, and we transformed those based on AKDC, which created this mapping that we used. All the x values were divided by k, and we added d. All the y values were multiplied by a, and we added c. And that's going to be true for what we're looking at for these two functions. So for the one that we have over here on the left, first thing I want to do is describe the transformation. So I got to identify what letters we have. So out front we have a, and inside the bracket we have d. So our a value of 2 tells me this graph is vertically stretched. We have a d value of 3, which tells me it's translated 3 to the right. So what we're going to do is start with those base points that we have, that we created above, and then transform them based on these two values, a and d. So our basic points that we had above for x and y, negative 2, negative 1, 0, 1, and 2. Our y values were all these numbers cubed. And we're going to transform that to some new coordinates based on our mapping above. So for the x's, the two things that can apply to x are the k value, in this case there isn't one, well it would be 1, and the d value, which is 3. So it would just be x plus 3. For y values, they get multiplied by a, and we add c. There is no c in this case, so we just have them multiplied by a, which is 2. So I'm going to come up with some new points based on these, or substitute those points into our mapping above. Our y values, multiply them all by 2. So when I plot this onto our grid down below, you're going to see that it's going to be a twist. with the transformations applied that we described above. It's going to be a little bit more stretched than the original, and it's going to be shifted 3 to the right than the original parent function. So I'll put these ones on our graph, 1 and 16, or negative 16. Off our graph, but a little bit low. And we got 5 and 16. Oops. Something that looks like that. Remember what the base equation looked like above. I'll just draw a little rough graph of it here, but it looks something like this. So I can see that that one's been translated to the right. I can see that it's a little bit more stretched than the original graph that we start with. Next, what we're going to look at is a quartic function over here on the right. So we're going to treat it the same way. The difference with this one is it has a k value, but that k value has been distributed inside, so I need to factor it out. So if I'm just working inside this bracket over here, I'm going to factor out a half. If I'm factoring out a half, I'm going to have 2 divided by half, because that's what happens when we factor, is we divide. 2 divided by half, we get 4. So what we're going to do is just list all of our transformations that we have here. Just like a quadratic, the only thing that's different is the exponent is 4. A is equal to the value I have out front, negative 1. K, we talked about it earlier, is half. D in this case. Remember, D is what's inside the bracket, but it's what you subtract from x. So x minus negative 4 is the same thing as x plus 4, so D is negative 4. And C value is what we have on the end. In this case, works out to be 3. So if I'm describing the transformations, I can start over here on the left. It's A is negative 1. I know that there's a vertical reflection. K is half. I know that's a horizontal stretch by a factor of 2. D is negative 4, so I know that that's been translated 4 to the left, and C is 3. I know that's translated 3 up. So translate 4 left and 3 up. So what we're going to do is we're going to take the base points for a quartic function, as we have above. So I'll list them down here. You know there's an x and there's a y. We know it was negative 2, negative 1, 0, 1, and 2. And it's just these numbers to the power of 4. 16, 1, 0, 1, and 16. We're going to transform these based on our mapping. Now, in this case, we have letters for each of them. So remember, x is divided by k, in this case half. So x divided by half is the same thing as multiplying by 2. Dividing by half, same thing as multiplying by 2. We have a d value of negative 4, so I'm going to subtract 4. For our y values, we have a negative 1 for my a value, so I'm going to have negative 1y. We're going to add 3. That's our c. So I'm going to put these values that we have in our basic points on the left into our mapping to see where we end up with our new points. So when I put in negative 2, negative 8, negative 1, 0, when I put in 2, 0. Same goes over here on the right. I'm going to plug in my values, 16, 1, and 0. 1 and 16 are there twice, so once I figure them out once, I know what it's going to be for the other one. Negative 13, 2, 3, 2, and negative 13. So I'm going to plot these onto our grid, and we're going to see where our new function would be. So negative 8 and 13 is a little bit off the graph, but I'll imagine it to be over here. Negative 6 and 2. Negative 4 and 3. General sketch would look something like that. So based on what our basic parabola looked like above when we did it, we know that it kind of looked something like this. Oops. So I can see that one's been shifted to the left. I can tell it's been shifted up. It's also been reflected, and it's been horizontally stretched a little bit wider than the original. So same rules apply to our normal transformations that we were using for any of the functions that we've worked with in the past. AKDC still applied the same way, as long as we start with some base points. The last thing that we have to do is talk about x-intercepts. So one thing that we know, for the ones that are on the left, when we have an exponent of an odd value, so cubic functions, for example, I know there's going to always be at least one x-intercept because it's a twist. It's always going to have to pass the x-intercept x-axis somewhere because the end behavior is on opposite sides, whether it's from top to bottom or bottom to top like this one. For the cubic function, or for the quartic functions over here on the right, I know that they could have multiple x-intercepts. In this case, you could have two, like this one over here on the right. You could have one, like the basic function, or you can have none when they're written in this form. So let's have a look down below. Let's look at this cubic function here. It says determine the x-intercepts. So if I want to find the x-intercepts of this, I know there's going to be at least one because the end behavior is on opposite sides. I know that because it's cubed. When we find out our x-intercepts, that happens when y is equal to 0. So I'm just going to plug in 0 for y and isolate. That'll tell me where my x-intercept would be. So when I isolate, I'm going to bring 16 over to the left side. It's going to be positive 16. I'm going to divide it by negative 2. And now I have a cube. In order to get rid of that cube, when it was square, we could square root. When it's cube, we can cube root. So there's only one answer to a cube root of negative 8, and that's negative 2, because negative 2 times negative 2 times negative 2 is equal to negative 8. And cube root and cube cancel each other out. And I bring one over to the other side, and I find out that my x-intercept in this case happens to be at negative 1. So I have an x-intercept at negative 1 and 0 when it's written in this form. Same goes for the one over here in the center. What we have here is we have a quartic function, and if I'm trying to find out the x-intercepts here, we know there could be more than one. There might not be any, but there could be more than one, could be even one. We're going to treat it the same way. I'm going to put 0 for y and try to isolate. I'm going to bring 12 over to the other side, and when I bring 12 over to the other side, it becomes positive. And then I have this 3 over 4. In order to get rid of that 3 over 4, I can multiply by its reciprocal. Multiply by 4 over 3 on both sides. Right, it's like multiplying both sides by 4 over 3 because they'll cancel out. That'll leave me with all of this to the power of 4. So I need to evaluate what we have over here on the right. I'm sorry, on the left. 12 times 4 divided by 3, 16. Now over here on the right we have it to the power of 4. In order to get rid of the power of 4, I have to take the 4th root. The 4th root of 16 has two answers. Positive 2 and negative 2, because 2 times 2 times 2 times 2 is 16, or negative 2 times negative 2 times negative 2 times negative 2 is also 16. So I know the answer is both positive and negative 2. And then it's just using algebra to get x by itself. Multiply both sides by 2 in order to get rid of that half. Bring 5 over to the other side. When I do that, it becomes negative. So now there's two answers for x. If I have positive 4 take away 5 is negative 1, or negative 4 take away 5, negative 9. So two x-intercepts in this case, negative 1 and 0, or negative 9 and 0. It's going to cross twice. It's a U shape. It's a to the power of 4, a quartic function. Lastly, what happens with the one that we have over here on the right? So this is another quartic function. I know that I could have 2, like the one we just saw. I know that I could have no x-intercepts. So we treat it the same way. We don't know headed in whether there's x-intercepts or not, but we try to solve it the same way each time. I'm going to bring 40 over to the other side so it can come positive 40. In order to get rid of that negative 5, I'm going to have to divide by negative 5. When I divide the left side, we end up with negative 8 is equal to x plus 6. And then I try to get rid of the power of 4 by taking the 4th root. But over here on the left side, we can't take any even root of a negative number. Just like you can't square root a negative number, you can't take the 4th root of a negative number, 6th, 8th, 10th. So no x-intercepts. So this would be one of those U shapes that would be either above or below the x-axis. Like so. One of those two, when there are no x-intercepts. And that's really all it comes down to for this section here, just dealing with transformations and how do we find out our x-intercepts when they're in this form, written like our transformation form that we're used to see. So some practice questions that you can look at are down at the bottom here. On Wednesday, I'm going to post a problem set for you to work through and take a picture of it and submit it on Google Classroom by the start of the following week's lesson, so by the following Monday. And that's it. So hopefully